We're all familiar with the phases of matter, solids, liquids, and gases, and how they behave differently. A solid is generally fixed in its shape and size or volume. A liquid will usually take the shape of its container, but will remain fixed in its volume because it is relatively incompressible. Lastly, a gas will expand as far as the confines of its container will allow, and can be compressed easily compared to the other two states of matter. We also have another state of matter called plasma. Liquids and gases are able to flow, and so we collectively refer to them as fluids. And fluids generally exert pressure on objects they come in contact with, including other fluids. We define pressure as the perpendicular force per unit area. So a fluid is able to exert force on other objects, and this force is usually a result of an external force acting on the fluid itself, or a result of its own weight. Pressure is measured in newtons per meter squared, which is also called Pascal, and it is a scalar quantity, meaning it has no direction, just magnitude. The amount of pressure a fluid is able to exert may vary from point to point within the fluid, but at a particular point, the pressure exerted by the fluid is the same in all directions in the static case, meaning when the fluid is at rest. To explain this further, let's take a look at a vessel containing a small amount of liquid. The amount of pressure exerted by the fluid at the point near the surface will be different from the pressure at the point closer to the bottom. Usually, the pressure in a fluid increases as we go deeper, and I'll explain why that happens soon. But for now, what that tells us is the liquid exerts a much higher force per area on the vessel at the bottom than at the top. But this pressure exerted by the liquid at the bottom is the same in all directions. Now we're going to talk about what creates pressure in fluids, specifically liquids in static or equilibrium conditions. The first instance we're going to consider is a fluid under gravitational influence. A fluid has mass, and therefore it has weight, which is a force, and this creates a pressure within the fluid. Let's take a look at this vessel, which initially contains some amount of liquid. We're now going to add some more of the liquid so that we have an additional height h of liquid. This extra amount of liquid has weight and is supported by the remaining liquid below it, which is what we had initially. We can calculate the mass of this extra liquid by multiplying its density by its volume, since density is defined as the mass per unit volume. The volume of this extra column of liquid can be written as the product of the cross-sectional area of the vessel and the height h. So the mass of this extra amount of liquid is equal to the density of the liquid multiplied by the cross-sectional area of the vessel multiplied by the height h, which gives us rho ah. And its weight would simply be the mass multiplied by the acceleration due to gravity, g. Also keep in mind that realistically, when we pour our extra liquid, the two samples are going to mix and there's going to be no obvious partition or distinction between the two samples. I'm only making the separation to aid this explanation. So going back to what we have here, the lower portion of fluid now supports the entire weight of the upper portion. And if we apply Newton's third law at the partition, we'll see that the lower portion of fluid supplies a force which is equal and opposite to the weight of the upper portion of fluid in order to maintain equilibrium. This is what creates the pressure at this point in the fluid. And the magnitude of the pressure exerted by the fluid at this point can therefore be calculated by dividing the force by the total area. This relation P equals rho gh gives us the pressure in a stationary fluid with constant density at any point, where h is the height of fluid above that point. And the reason why it's applicable at any point in the fluid is that, regardless of the height or level we choose, the fluid up to that height will always support the weight of whatever amount of fluid is above it. We can imply from this that the deeper we go, the higher the fluid pressure is, since there is more weight to support. And at the bottom, pressure is the highest, since the weight of the entire fluid has to be supported. Also, at the top surface of the fluid, there is no pressure from the weight of the fluid. Another thing to note is that, although the weight points vertically downwards, the pressure at any point in the fluid acts in all directions. Let's take a point close to the inner surface of the vessel, for example. The pressure P at this point, no doubt, is directed upwards to support the weight of the rest of the liquid above it. But it also points sideways and downwards and everywhere else in between, in all directions. So the pressure P is also exerted on the inner wall of the vessel and on the surrounding fluids. Apart from gravitational influence or weight, pressure can also be created in a fluid by an external force acting on it. Let's consider this setup where an external force pushes on the surface of a liquid contained in a vessel in the absence of any gravitational force. If we cut the fluid at any point and analyze the forces on the section of fluid in contact with the disc, we'll see that there's an equal but opposite force to the applied force supporting this section of fluid. This support is provided by the rest of the fluid in the vessel, and this is how pressure is created. This pressure is equal to the force divided by the cross-sectional area of the vessel and is the same at any point within the fluid. This is because if you section off the fluid at any point, the same amount of force still has to be supported, and so the same amount of pressure is generated. Again, this pressure is the same in all directions at any point. If the fluid was under the influence of gravity and had weight, the total pressure in the fluid at a particular point would then be the sum of the pressure due to the fluid's weight and the pressure due to the external force, where h is the height of the fluid above that point. This is a very well-known principle called Pascal's principle, and it states that if an external pressure is applied to a confined fluid, the pressure at every point within the fluid increases by that amount. And this principle holds true regardless of the shape of the container or vessel. The planet's atmosphere is made up of gases, which we classify under fluids, and so it exerts pressure on every object it comes in contact with. And this pressure varies from place to place depending on factors such as altitude, weather conditions, and wind velocity. But at sea level, the atmospheric pressure on average is equal to 1.013 times 10 to the power of 5 Newton per meter squared, or 1.013 times 10 to the power of 5 pascals. This value allows us to define another unit of pressure called the atmosphere. So 1 atmosphere equals 1.013 times 10 to the power of 5 Newton per meter squared, or pascals. Another unit of pressure sometimes used is the bar, which is defined as 1 times 10 to the power of 5 Newton per meter squared. So we can also say that 1 atmosphere equals 1.013 bar. If we have a vessel containing liquid where the liquid is exposed to the atmosphere at its top surface, the atmospheric pressure acts as an external pressure on the fluid, and the total pressure at any point in the fluid, according to Pascal's principle, will be equal to the sum of the pressure due to the weight of the fluid above that point and the atmospheric pressure.